Hey guys, it's Dr. Calkins again. Today we're going to look at some week 9 material with intermolecular forces. So when we talk about intermolecular forces, we want to make sure that we think of something like an interstate. An interstate would go from state to state to state. So an intermolecular force for a molecule would go from molecule to molecule to molecule. So it might be easiest to start from the weakest and move our way to the strongest, because what you're going to see is lots of things have low boiling points. So you'll see questions like that. And then you're going to see things that have very high boiling points. And we need to be able to figure out who's who. So as we look at examples like this, we need to first think, does it have metals or not? We often say in class that if somebody throws a rock at your head, which one hurts? The rock typically doesn't hurt because it's made of metal. Your head hurts because those tissues are made of non-metals, very easy to tear, very easy to break. The only thing that's going to stand a chance against that rock is your bones, but again, they have metals. So a lot of that strength is what's going to give you that high boiling point. So we're going to see a lot of metals in this kind of region, and then non-metals in this lowermost region. So let's start with our weakest held together kinds of molecules, and this is really just everybody. So everything will have these. These are called dispersion forces. We call them dispersion forces because they disperse. They have that ability to, as they congregate, kind of like a snow globe, as you'll see in some of the lab examples, those electrons can gather together, and when they do, they have a little bit of negativity that can be attracted to other positivity from another molecule, but as soon as they do, they probably disperse and that attraction is broken. These are also called London forces, so we make the joke of the nursery rhyme, London Bridge is falling down, because these forces are always breaking. So the reason we say everything has them is because everything has electrons. And if everything has electrons, they're going to have the ability to do this. It's just that if you have something weak, we only care if you have something stronger. And whatever you have that is stronger is going to be your dominant force. So we're going to be looking for those dominant forces. The only time that we really care about London forces at all is when we're nonpolar. If we're nonpolar, that just means that we didn't have that 0.5 in electronegativity kind of idea. So a lot of our gas molecules are typically dispersion force based because they're nonpolar, like a lot of our small hydrocarbons, a lot of our perfectly canceling oxygen O2 molecules, nitrogen molecules, even the two-way tie carbon dioxide molecules fit in this category. A good idea to think about this is kind of an analogy. This would be like a sticky note. It's very easy to peel on and peel off because that glue is not very strong. Another analogy that we're going to run with is like a garage. These three would be representative of our garage, and this would be like the tricycle. Because if you look in everybody's garage, they probably have a tricycle. And if you were to look in somebody's garage and see a tricycle, you don't really care because it's not that special. As we move across to something a little bit stronger, we're going to see dipole forces. And in order to have dipole forces, you need a dipole. Hopefully you remember how to find those. You have to be polar. So for polar, that just means that we are 0.5 or larger in electronegativity difference, and now we have an attraction from two molecules that have that partial positive, partial negative kind of attraction. This would be more of a Elmer's glue, so pretty strong, but definitely not super strong. Better than sticky note for sure. And a tricycle would be the weakest, but this would be more like a motorcycle. And the reason we use that is because not many people have a motorcycle in their garage. It's a lot more powerful than a tricycle for sure. But when you see a motorcycle, it might catch your eye because, hey, it's a little bit more powerful than what you would normally see in a particular garage. A little bit stronger of a glue, so to speak. So you have to be polar to be in this category. And what we're seeing is, if you're in this category, we're now seeing that you can also be in this category with the right kind of atoms. because you have electrons, but now you have the special kind of electrons on some, say, bullies that help you out and give you some polarity. Then the cream of the crop that we're looking for that is everywhere in the human body is hydrogen bonding. A lot of students associate this with a bond to hydrogen, but that's not the case. We do look for certain bonds like an N to an H, an O to an H, or an F to an H for this to exist. When this happens, it's because we have these huge bullies at 4.0, 3.5, and 3.0 attached to somebody small like a 2.1 hydrogen. So huge differences there, close to 2 almost, so 1.9, a 1.4, and a 0.9. Superpolar, so that's the difference. We're specifically the 3 biggest bullies attached to the biggest WIMP in the sense of that analogy. And that's why we're so polar. We have the most partial positive charge that is capable for molecules before they just split apart into ions. So definitely we're looking for that kind of 0.9 or 1.4 or 1.9 kind of difference in electronegativity, much, much higher than the 0.5 needed. Because these are superpolar, we would call this super glue. Super strong, strongest that exists. And this would be like the Ferrari. Not many people have a Ferrari in their garage. I would even, in this case, not even want one. I prefer a Ford over a Ferrari any day. But in any case, the same idea that you have is rarely will you see a Ferrari. So watch out for those 3 specific bonds, because if you have them, it's important. It's going to make you super strong in that situation. We also want to pay attention to this and how it applies to our last chapter. As we look at, say, some of these groups down here, I'm going to move up just a little bit. This is going to be our hydrocarbons. Those are going to be dispersion because they're nonpolar. So the alkanes, alkenes, alkynes, and arenes, so single, double, triple bonds. The arene that looks like a ring, it's going to be in that category. When you have a dipole only, you're going to be carbonyl containing. So anything with that C double bond O can be in this category because that C double bond O is going to have a 1.0 dipole. So this is going to put us in our aldehydes, ketones, esters, acids, amides. It's also going to have the carbon to oxygen or carbon to nitrogen bonds. So we're looking at things like alcohols, phenols, ethers, amines, and then carbon to fluorine, so even some organic halides, carbon chlorine barely reaches in there at a 0.5 kind of difference. Carbon bromine, carbon iodine, they're going to be back over here based on our math, because that's only going to be a 0.3 or 0.5 or a 0 difference, so 0.3 for bromine, a 0 difference for iodine compared to carbon. And then if you're hydrogen bonding capable, what's most important is to recognize those are our alcohols, because those are ROH. Also could be a phenol with an AROH. Definitely the carboxylic acids, those are the COOH. We have the amines and amides. And those are the NH2 kind of groups, with or without the carbonyl. So those are what we're looking for. Again, the amide has a double bond, letter D. Amine does not. So those are the things to kind of aim for in your homework. So the last couple categories go a little quicker. This is where we toss in some metals. So I'm going to zoom kind of back up a little bit. Our next category of strength is metallic. The reason there's a dotted line here is because it also kind of overlaps with ionic. To be ionic, you have to have a metal positive and a non-metal, or a group of non-metals that are negative. To be a metallic, you're just a metal with no charge, which is unique that it's in that location at all. A lot of times, temperature-wise, we might look at, say, about 250 Celsius in this range. So anything less than 250 this way, anything higher this way. And this will get you up to, say, maybe 1500 degrees by the time we get to the, so that's just a generic range of what to look for. Metals like iron and gold definitely take a lot to melt them up. If you watch shows like Forged in Fire where they're melting iron, it takes a tremendous amount of heat. Ionic, remember to look for the IDE, the ATE, or the ITE. Great ways to recognize some of those binary IDEs or those ternary ATE or ITE kinds of compounds. Very strong because you have strong attraction. The reason these are stronger than, say, down here is because these are the ones that had partial positive, partial negative. These have real negative, real positive, so they're real strong. And then our last category, the strongest of all, is what we would call a covalent network. So a lot of them, these are called just network solids. And these are things like diamond and graphite and quartz. Those are really the ones that show up in the homework. Diamond's super strong because it has just carbon atoms and they're just covalently bonded. There's no intermolecular force because you're breaking bonds, you're not breaking attractions. Graphite, same way. Carbon atoms, you have to break bonds, not attractions. Here you have to break an attraction, so it's weaker. Here you have to break partial attractions, so they're much, much weaker. And that's the kind of scale we see. These are going to get up well into that 3,500 kind of plus range. Mathematically speaking, if you wanted to put a number on it, we have about a 1 here in scale. This is about an 8. So it's about 8 times stronger on average. This is about a 16. So hydrogen bonding is about twice as strong. Covalent bonds themselves, which aren't attraction, they're actually bonds, that's about 400. And this is talking about kilojoules of energy. So that kind of gives you a numerical perspective, different from, say, our analogies that we used before. So hopefully, this is going to be the only video for this chapter because this is pretty much the entire thing. Hopefully this gives you an idea of what to look for in your homework. Just remember that if you have a low boiling point, it's because you're weak. You're easy to break apart because your glue is very weak. If you have a high boiling point, it's because you're very strong. Maybe so strong that you don't even have attractions, you have real bonds to break instead. So good luck on your homework. If you have questions, feel free to send them my way.